Hi, welcome to the second part of the MRI series video. In this video, we will look into the components in MRI, types of scans in MRI, and Hlelium Less MRI machines. If you have not seen the first part of the MRI series video, I would like to request that you begin with that part first. Let's begin with the components of MRI machines. The major components of an MRI scanner are the main magnet, which polarizes the sample, the shim coils for correcting the homogeneities in the main magnetic field, the gradient system, which is used to localize the MR signal, and the RF system, which excites the sample and detects the resulting NMR signal. The whole system is controlled by one or more computers. The first component is magnets in the MRI machine. The magnet is the largest and most expensive component of the scanner, and the remainder of the scanner is built around it. The strength of the magnet is measured in Teslas, or T. Clinical magnets generally have a field strength in the range of 0.1 to 3.0 T, with research systems available up to 9.4 T for human use and 21 T for animal systems. In the United States, field strengths up to 4 T have been approved by the FDA for clinical use. There are different types of magnetic principles which are used, like permanent magnet, resistive electromagnet, and superconducting electromagnet. The second component is shims in the MRI machine. When the MR scanner is placed in the hospital or clinic, its main magnetic field is far from being homogeneous enough to be used for scanning. That is why, before doing fine-tuning of the field using a sample, the magnetic field of the magnet must be measured and shimmed. After a sample is placed into the scanner, the main magnetic field is distorted by susceptibility boundaries within that sample, causing signal dropout, regions showing no signal, and spatial distortions in acquired images. For humans or animals, the effect is particularly pronounced at air tissue boundaries such as the sinuses, due to paramagnetic oxygen in the air, making, for example, the frontal lobes of the brain difficult to image. To restore field homogeneity, a set of shim coils is included in the scanner. These are resistive coils, usually at room temperature, capable of producing field corrections distributed as several orders of harmonics. After placing the sample in the scanner, the field's shimmed by adjusting currents in the shim coils. Field homogeneity is measured by examining an FID signal in the absence of field gradients. The FID from a poorly shimmed sample will show a complex decay envelope, often with many humps. Shim currents are then adjusted to produce a large amplitude exponentially decaying FID, indicating a homogeneous field. The process is usually automated. The third component in MRI systems is the radio frequency system. The radio frequency, or RF, transmission system consists of an RF synthesizer, power amplifier, and transmitting coil. The coil is usually built into the body of the scanner. The power of the transmitter is variable, but high-end whole-body scanners may have a peak output power of up to 35 kilowatts and be capable of sustaining average power of 1 kilowatt. Although these electromagnetic fields are in the RF range of tens of megahertz, often in the shortwave radio portion of the electromagnetic spectrum, at powers usually exceeding the highest powers used by amateur radio, there is very little RF interference produced by the MRI machine. The reason for this is that the MRI is not a radio transmitter. The RF frequency electromagnetic field produced in the transmitting coil is a magnetic near field with very little associated changing electric field components, such as all conventional radio wave transmissions have. Thus, the high-powered electromagnetic field produced in the MRI transmitter coil does not produce much electromagnetic radiation at its RF frequency, and the power is confined to the coil space and not radiated as radio waves. Thus, the transmitting coil is a good EM field transmitter at radio frequency, but a poor EM radiation transmitter at radio frequency. Let's look into different types of scans in the MRI system. There are a variety of different MRIs available. The most common MRIs include functional MRI. A functional MRI, or FMR, tests brain activity. The images indicate whether there are any issues present that may predict or diagnose a stroke. A doctor also orders an FMR for brain mapping. Brain mapping is essential for brain surgery or for detecting epilepsy or tumors. Cardiac MRI. A cardiac MRI produces detailed images of the heart. Your doctor will call for a cardiac MRI to diagnose your condition so that a treatment plan can be devised. In addition to the heart, the blood vessels surrounding it are also examined. The information gathered is used to determine heart function. MRI of the breast. Patients who are at high risk for breast cancer are candidates for an MRI. While it is a non-invasive procedure, doctors may order an MRI-guided needle biopsy of the breast. The MRI will detect breast cancer and provide information on progression and location of the tumor. Magnetic resonance venography, or MRV, is combined with contrast dye to produce clear images of internal organs and other structures inside the body. The dye highlights the veins so that they appear translucent and show up well in the images. Magnetic resonance angiography is similar to an MRV. It combines images with an intravenous contrast dye, but focuses on blood vessels instead of veins. The physician will be able to evaluate the blood vessels that run through the heart and soft tissues of the body. Non-contrast MRI. Some patients may be unable to tolerate contrast dye. This is especially true for patients who have renal problems. Historically, these patients could not get MRAs performed. However, it is now possible for all patients to get MRAs using advanced diagnostic technologies that eliminate the need for dye without compromising on clear images. Open high-field MRI. Being closed in is a fear that some patients have in regards to an MRI exam. Patients who are claustrophobic don't like the design of an MRI machine that is enclosed. Other patients may be obese or suffer from post-traumatic stress syndrome, preventing them from feeling comfortable in the machine. For these patients, open, high-field MRIs are a better choice. Let's end this video with Hlelium Less MRI machines. Critical in the use of high-field MRI scanners, which use helium to cool the superconducting magnets to 4 Kelvin or -269 centigrade, the declining availability of helium is causing waves of concern across the research and medical field. Standard high-field MRI scanners not only require hundreds of liters in which to bathe the superconducting magnet, but need regular top-ups as helium leaks away. With declining reserves and increasing prices, finding an alternative solution was critical. In response, UK-based MR Solutions has led the way in developing helium-free, commercial, high-field, using a superconducting magnet, MRI systems in preclinical systems. The only way to keep MRI magnets currently in clinical use that cold is by using thousands of liters of liquid helium mined from below the Earth's crust. Magnets with Hlelium technology are designed to be less dependent on helium, much easier to site, and eco-friendly. Thanks to Hlelium technology, hospitals would no longer need extensive venting that often necessitates sitting a magnet in a separate building or newly constructed room. Additionally, a Hlelium magnet would not need any refilling during transportation nor throughout its lifetime. Therefore, when the Hlelium technology is integrated into a commercialized product in the future, it could make MRI more accessible and less expensive to site and operate. This was the last video of the MRI series videos. We always try to keep our videos simple about medical devices without going into deep engineering studies so you can know about the devices on the go. If you like our content, do subscribe to the channel and give this a thumbs up. See you guys in the next video.